homogeneous shear, and we see that after a longish wait, we start to get large-scale magnetic fields, which are quite strong of partition strength. And we find that the growth rate of this field is proportional to the shear rate, which is the result which has also been obtained from force turbulence, but which does not have a unique theoretical explanation so far.
Is it something similar to shear current dynamo?
Well, shear current effect is one of the explanations that could be. This is not the only one. Then we could have actually in this case we have stratification, so we have also an alpha effect. So we cannot really distinguish the driver of the dynamo.
But you do know eta 2-1 in this case.
Yes, we do know the component of the eta tensor that is responsible for the shear current effect, and that does not have a unique sign. So it changes sign as a function of depth. So at places it could drive the shear current dynamo, and other places not. And furthermore, its value is highly variable, so it's not altogether clear that these results are statistically really significant.
Have you got diagonal waves in this installation?
No. And similar results have been obtained by other authors with more complicated shear profile. We have done similar things, essentially criticizing the.
Excuse me, I don't know if you're going to explain, but I don't quite understand what you say about web geometry.
This will become clear.
Okay.
Magnetic bundle number?
In this case, it's 5.
5.
But we have actually done a survey where we changed the magnetic bundle number, and we can get a large-scale dynamo. Well, essentially, there's a critical Reynolds number, magnetic Reynolds number, which is close to 1 for the large-scale dynamo. So we get a large-scale dynamo also for Prandtl number of 0.1.
Oh.
What can be the size of this?
Well, this is all in non-dimensional units. So the depths.
In density scale heights.
Okay, in density scale heights we have something like 3 density scale heights in the convectively unstable layer, because we have a stable layer below as well.
So the total density stratification, that's a factor of
About 30, so a little less than 30.
the total top and total bottom.
Yes.
Density scale heights.
No, this is the density contrast.
Oh, density contrast.
Yeah.
It's only half because magnetic field only.
Because we have only. Oh, you mean this one?
Yes.
Yeah.
Okay, this is more complicated because there we have this sinusoidal shear, and this is really a complicated stuff. So I don't want to get into that. So read that paper.
Only that was a particular, we are reproducing the Hughes and Proctor paper. It's a one-to-one comparison. That's
Yes.
why we
So
did that.
the thing is that on this side of the box you have a large alpha effect. On that side of the box you don't.
I mean,
you have a
Hughes and
small-
Proctor have been saying there's no alpha effect.
Hmm?
Well, we saw similar feature in Igor's simulations, and I thought maybe it's a feature of the pencil code. When magnetic field is on this side.
I mean,
Okay.
we are saying it should have been in Hughes and Proctor, and they may have not even noticed this because they just show power spectra.
Yeah, they don't show the actual magnetic fields.
So then they didn't see that.
Does your alpha effect change sign?
Yes.
You mean in this case,
Yeah.
with the sinusoidal shear? Yes. I mean, on different sides of the box,
Yeah.
it can have different sign. If the shear
It's
is
a
strong-
boundary? Is it a boundary effect?
Periodic.
Yeah, it's periodic in horizontal directions, but we have very weak stratification here.
Mm.
So the inhomogeneity of turbulence is due to the vertical boundaries.
Yeah.
But I better move on because this is not the thing that I want to talk about.
So consider this a local dynamo, right? Right. So
Right.
we see there's a scale size of 600 kilometers.
It's not scalable. It's a magnetic field is much larger than the cells.
Right, and the scale height at the base of the convection zone is
What is that
50,000
convection
kilometers.
cell? If it's only
But you see, there's many convection
Yeah, you
cells.
see, you essentially see here, this is actually without any shear, this is only rotation. So you see here these convection cells, so we have something like of the order of 100 convection cells.
you don't have accumulation right what you have talked about.
Well, in this case, the rotation is very rapid, so the convection cells are smaller.
So what was the number here?
Rossby number is, okay, it's of the order 0.1.
So it's not so far for comparison with solar situation, of course.
Yep,
This Rossby number.
Ross
Креволис.
correlates.
What Креволис number?
Rossby number will
Can you calculate?
Well, 10.
10.
If Rossby number is 0.1, then the Coriolis number is
You can always multiply and divide by 2 pi if that is better for you.
Okay, proceed.
Okay, so this is just to demonstrate that even without shear you can have a large scale dynamo. And this is really then the only effect that could explain the generation of large scale field is the alpha effect. So this would be an alpha squared dynamo with numerical manifestation of an alpha squared dynamo. And okay, maybe I don't go into the scale separation business. So what's the problem with these models? Well, it's obvious that we cannot model, for example, the solar dynamo in a Cartesian box which is periodic. So what we really need is spherical geometry, and what we also need is, or what we then can, in principle at least, get in this geometry is a more realistic representation of the differential rotation. Because in the local models we always have to impose this externally, but when we go to spherical geometry we can, at least in principle, generate this software system. And of course there are other people who are already doing this, and these are results with the Ash code by Matt Browning, Mark Misch and collaborators. And these models are fairly advanced now, so they can reproduce the seismic rotation profile, at least in many details, although they have to do some tricks to get it right, to impose some kind of latitude-dependent entropy gradient base and stuff like that. And it's also possible to, this is the magnetic field near the top and then in the overshoot layer. And the problem here is that the large-scale dynamo seems to occur only in the overshoot or in the Tucker-Fine region, which is a bit of a problem if you consider the sun. And here also the field strengths are of the order of a few kilogauss, not a few hundred kilogauss.
And what's the period of this dynamo?
I mean, this is non-oscillating. And then similar results have been obtained from more rapidly rotating models, and there you actually see large-scale fields also in the convection zone itself. And but as far as I can remember from this paper, these were not really, well, they did see sign changes of the magnetic field, and they didn't appear to be too coherent in time. And now the question is, do we actually need a full sphere to model the dynamo? If we look at where sunspots occur, so we have this strip from -40 to +40 degrees latitude, where most of the action seems to be going on. And also, the magnetic field of the sun is mostly axisymmetric. Sasha is not agreeing, but
Not at all.
well, locally, maybe not.
No, I mean, of course. I mean, you would be be saying that here's polarity law is violated at certain latitudes, longitudes. Is that the case? That's what you're saying. If it's non-axisymmetric, that means the toroidal field is changing its direction at different longitudes. Is there strong evidence of that?
No, I mean non-symmetric because it's not uniformly distributed longitude. You don't, to make a field non-symmetrical, you don't need to change sign. It may have the same sign, but amplitude is quite different. Depends on longitude. And we know it's not symmetrical. Like I showed these pictures, when we have
Yeah, but if you say not at all, if you say it's not at all axisymmetric, then that's not a correct statement.
No.
I mean, the majority of the field is
What's the definition of asymmetrical?
Maybe we should really
Maybe we
postpone
have a
that.
different definition of
We should
asymmetrical.
discuss this.
Okay, we should postpone this.
Because the normal definition doesn't depend on field angle. That's what people call
That's-
symmetrical,
that's-
right? And
that's-
in mathematics and
Yeah.
physics.
Okay,
Let's
let's
have a different
let's
definition than something
postpone
else.
this discussion because otherwise it's very interesting. So, what we then propose, we don't need the full latitude and longitude ranges. Then, what if we just take part of those? And this is what we call the wedge. So, we take a part of the latitude and then also the part of the longitude. Here I try to make ideal do what I wanted it to do. It almost did it. So you see that we model this part here. So this is now, actually it's not exactly the same as here. We have 120 degrees, yes, in longitude and latitude. On the latitude we have stress-free for the velocity and then perfect conductor for the magnetic.
And in longitude, you get up anyway, right?
Yes.
So your manifold is more compact in that sense, in the mathematical model. The compactize your manifold.
You could say that. Yes. And okay, so this is the basic geometry that we are using. And okay, so then we do some hydrodynamical runs. And this is now this is not a very good picture in hindsight. This is azimuthally averaged components of the velocity, radial, latitudinal, and this is now the rotation for omega. And then we have kinetic helicity. And of course for no rotation we do see some large cells here, but there is no new rotation of course. And for slow rotation we get a really strong meridional flow and strong differential rotation, and but actually it turns out that this one, if we include magnetic fields, it doesn't act as a dynamo. And for strong rotation here, Coriolis number is 2.5 in our units, so that's without the 2 pi factor. Then we see the Taylor-Proudman balance setting in, so everything is aligned with the rotation vector. And we do see equatorial acceleration. And we also do see some large-scale structure in the kinetic helicity. So we have negative kinetic helicity in the north and positive in the south, at least close to the surface, which would mean if we use this as a proxy of the alpha effect, we should have a positive alpha in the north and negative in the south.
But you change sign in depth.
Yes, there is a sign. At least the kinetic helicity changes sign as a function of depth. We don't actually know about the alpha yet. And what this means is that if we have a positive alpha and a positive radial gradient of omega, we should see a dynamo wave propagating towards the poles. And this is actually what we see. On the left you see the radial velocity near the surface, and the toroidal magnetic field also near the surface. And this covers something like, this animation covers about one cycle of the field. Maybe we play it again.
So, yeah, point out on the right-hand side the toroidal, the mine blue and the...
Right, so let's do this once more. So we start, so we have negative on average negative fields here at high latitudes. Then as things evolve, we have more and more positive fields there, and a negative strip is forming near the equator. And towards the end of this animation, we again have negative fields at high latitudes. And there appears to be a clear asymmetry between the different hemispheres, which we see in many simulations. And we don't really know what causes this, but then if we run, okay, that's wait. Run this is actually not the same simulation, but a very similar one. So here you see different field components here. This is the asymptotal average. So this is kind of like your butterfly diagram of the field. And here you see the toroidal field at different depths. This is the base of the convection zone, middle and near the top. So you see that in the beginning, for a long time, the southern hemisphere is stronger, and then towards the end, the northern hemisphere becomes more active.
What's the period in diffusion time, say? It's possible to say?
It's possible, but I would have to...
I think we estimated it was compatible with what one would expect from distributed mean field animal theory.
It took a couple of years in solar.
Yeah, exactly.
Yeah.
Certainly not longer than that.
Yeah. And, okay, then another thing. The point here is that this is clearly a distributed dynamo. Now you see here an animation of the toroidal field azimuthally averaged toroidal field. And you see, or begin to see, these belts of activity moving away from the equator. And this dynamo really works in the whole convection zone. But this oscillatory field seems to occur in this only near the equator, so near the poles we don't, or at high latitudes we don't really see this kind of activity. And in the overshoot layer, I should have mentioned that we also have an overshoot layer here which is convectively stable. There we see a magnetic field which doesn't change sign, or it does change sign but not with the same period. The oscillations are very unpredictable. Thanks.
When you put the equipartition, you've got profile of density in this problem?
Yeah, actually this equipartition value here is a volume average.
Volume.
And okay, that's one thing that I wanted to mention, that the mean fields here can be a few times the equipartition value. And if we believe, for example, Axel's table of yesterday, that the equipartition field strength in the solar convection zone is of the order of kilogauss, then we could expect to see, or that these large-scale fields are of the order of a few kilogauss in the convection zone.
That's maybe a bit too fast for the sun.
Yeah, the rotation here is probably too fast for the sun, so it might be even less in the solar case. And we were actually extremely excited to get these results, and we thought, wow, this is something new, we have never seen this before. But, well, Gilman saw this already in '83, essentially the same, a very similar setup. He also had a system where he only took the, he didn't go all the way to the poles, to 75 degrees, I believe. And he saw very similar oscillations of the large-scale field. So it appears that this is nothing new in the end.
And should be here threshold in rotation rate?
Yeah, there is a threshold, and actually it's in the paper, but I can't remember it now. So we can look it up. So there's one more thing that I wanted to show. So there was, in the talk of Oleg yesterday, he showed a picture of the simulation of Ben Brown with these kind of reeds of large-scale magnetic fields that you can also see here. This is now V-phi close to the surface of the star, or whatever we want to call it. And we do see that there are strong strips of different side field. And what we do in our runs is that we have a boundary condition for the magnetic field, which allows only vertical field out of boundary. So if we really look at the boundary points, then this would all be Planck, but we do see the radial magnetic field. Now this is the radial component. And you can see here that there are something like bipolar regions here. So, yeah, one question is then how, if we believe that such things occur in some rapidly rotating stars, how do they actually look like at the surface? How we can detect those fields?
Because the horizontal field is 0, right?
Yeah, the boundary.
Yeah.
So this is something like 2 grid points below the boundary. Okay, I think that was all that I had, so I have some conclusions. So first of all, local models in Cartesian geometry can be used to study the excitation of large-scale dynamos, but stars are not very big boxes. And then if we do simulations in full spherical shells, then we can capture all the relevant physics. But it may be, in a sense, overkill because we require much higher resolution if we take a full sphere. If we can actually get away with doing just parts of the sphere. And what I presented here are just initial results which reproduce those of Gilman from '83 if you consider that it's promising that we can produce something which is already that old. And but the model still requires further refinement, and hopefully we can actually refine the model doing this. So, thank you.
Do we have time for some questions? Yes.
As I understood, you're considering turbulence in a spherical fixed geometry, right?
Yes.
I wonder if you can do the same, changing the background. I mean, just going to positive curvature to zero
Changing the
curvature.
geometry on the fly.
Sorry?
Changing the geometry on the fly.
Yeah, I mean the background. Well, the fluid is.
I mean, there's different coordinate systems are possible, and of course, in free matrices, if you give it a metric, it can be implemented, yes.
Yeah.
One question?
I think the most weak point is in stress-free boundary condition, not far from box. You just kill turbulence somehow in this region. Have you tried something in that?
It's a pole, yeah?
Yeah.
That's right.
Yeah. Well, we haven't really tried any other boundary condition yet. So what would you suggest?
I mean, one sees, for example, the eddies move, they are more or less stationary, and one would expect them to be retrograde. One doesn't actually see that.
Maybe you can reproduce
Yeah.
this normal dynamo wave in this situation.
Your rotation more had a Taylor-Proudman
Yes.
structure. What about the shear? Positive at the equator or negative?
Positive.
Positive. So it must be. It was the same with Gilman.
Yes.
Yes, I think. Yeah.
Yeah, and it is true. With the sun, it is positive at the equator.
Yes.
What about the meridional flow? Did you find the meridional flow?
Uh,
One cell or more?
in this case, we have actually multiple cells,
Yeah.
which are not very visible here, but we do get multiple cells. This might be. This
Is
is
it
probably
in radius or in latitude?
both actually.
Both?
Yes.
Oh.
See, they are vertical cells.
Yeah, you can see here you have different cells here.
Aha. Then you have no chance.
But the problem, of course, is that if we want to learn about the sun, we would want to somehow make this rotation profile more solar-like. And then we probably have to introduce some unresolved effects like turbulent, anisotropic turbulent heat transport and stuff like that.
Okay, I think we are a bit short of time, so maybe some additional questions to Petra, like in the break or during the discussion this afternoon. So we've gone to the next talk, and I think I would think it's better like to have more discussion after the talk than during the talk. So maybe just try to when it's just short question during the talk, and so we have more time for questions after the talk.
But it's only, this is not okay. No, this doesn't work. No, this is not what my screen is showing. Last time I did No, I don't need to do anything actually, just comes on its own.
Ja, das zielt ja alles darauf ab, dass es lokal sich oder halb lokal irgendeine Weise bildet.
Das wäre fatal gewesen. Das macht die Frage. Das war die erste Frage. Ich habe dann alle seine Papers zurückgeschickt.
Nicht, dass ich echt wieder geben
Nie wirklich Antworten geben.
Das Linux, Linux now?
Ja.
Oder sonst ist es wenig Probleme und so weiter.
Then it's not Windows.
Yeah, that's what I did.
Und die haben daraufhin abgehört.
Ja, witzig.
Sorry.
Das ist nicht geklappt. Ja.
Ja, Müller. Entschuldigung.
Ja.
No, it's 5 minutes.
Because this is just showing a part of my screen.
If you have the answer for your question.
Okay, I asked about the separation of scales.
Well, if you look at this picture, We estimated there's.
Ja, das ist nicht, ich glaube, das ist logisch. Das glaube ich. Das kam auch nicht im Rahmen.
Yeah, it's clear that the scale of
Das
turbulence is
ist ganz wahrscheinlich. Das
Okay.
ist nicht so einfach. Man kann noch ein bisschen ausruhen.
Ja, überziehen, das kann man schon. Je nachdem, wo es zu ist. Also man kann schon Kudamm praktisch die Verlängerung des Kudamms später erzählen. Dann kommt der QB1 und dann kann man auch mit dem Mikro machen.
Okay, then we start. It's a second talk given by kapyla+chatterjee from here in Norwegian, but she was before at the Indian Institute of Science in Bangalore, and she will speak about helicity of sunspots from a dynamic model.
Thanks, one. And sorry for the technical problem. This work is actually a bit old, to be precise, 5 years old. And this was done when I was a new PhD student at IISc Bangalore with Orno. And the other people involved are Christoph from Yotos University and Dibbendu, who was at the time in Montana. And the reason I'm giving this talk now is I was very excited by the observations which Kirill was showing yesterday. And I thought about giving this talk about helicity calculation from flux transport dynamo model. So I had initially planned that I'll divide this talk into 2 parts. One is I'll talk about helicity of active regions from observations very briefly, and how do active regions acquire helicity, and are there any alternative methods of calculating helicity of sunspots from mean field dynamo models. I'm actually, when I'm talking about sunspots and active regions, I'm looking at them in different ways, because active regions are more complicated magnetic distributions rather than sunspots. And in the next part, if I have time for this, I'll talk about the distribution of helicity in a sunspot. That is, if you believe in the model that I'm going to talk about in part 1. And then about flux loss from the flux tube, which is rising through the convection zone. And flux loss from a twisted flux tube, which is rising through the convection zone. Now, this is the standard definition that the observers use for helicity. That is, the vertical current is proportional to the twist into the vertical magnetic field. And the sign of alpha, not to be confused with the alpha effect in dynamo models, is a measure of the handedness or the chirality of the field. And there are different processes which are responsible for generation of helicity in active regions. One of them is the dynamo process via the mean field alpha effect here. And there are various authors who have explored this. And in this, they basically have an equation for the dynamical evolution of the alpha effect in their models. And secondly, the dynamo process can indirectly also lead to helicity generation by accretion of colloidal flux by rising flux tubes. And this is the work I'm talking about right now. And then the third alternative is the sigma effect, which was proposed by Longthorpe, Fisher, and Betzer. In this case, the sunspots acquire helicity by interacting with the surrounding turbulence of the plasma. And then Johan van and Gong, they propose the effect of Coriolis force on flows in rising flux tubes give rise to twist. And then there were talks about differential rotation. Sasha was talking about differential rotation giving rise to twists of the flux tubes. Now, all these processes may not be mutually exclusive, and they may be operational at the same time. But the thing is that if we observe a cycle dependence, the solar cycle dependence on the helicity, then more often than not, it will be easier to believe that the dynamo process is responsible for generation of that helicity. I mean, the most part of that helicity happens because of the dynamo process. Now here are this is just one slide which I've kept for observations because Curie talked about observations in detail. This figure is from Canfield and Petzer. They analyzed the solar magnetogram from Mies Solar Observatory from 1988 to 96, and they found that predominantly most of the active regions in the southern hemisphere have positive helicity, and those in the northern hemisphere have negative helicity. So statistically, they said, statistically the number of active regions they analyzed, they say that 74% of the active regions in the southern hemisphere had positive helicity, and I think something like 66% of the active regions in the northern hemisphere had a negative helicity. And this is the more later figure from Sokolov et al., where they have tried to study the cycle dependence of, they have studied the helicity of active regions over one solar cycle, that is the 11-year solar cycle. So this is what I will try to explain now. Why is it that we should expect negative helicity in the northern hemisphere and positive helicity in the southern hemisphere? Now, in a Babcock-Leighton dynamo model, the poloidal field, which I denote by A, is created by the decay of tilted bipolar active regions. Now, suppose this is the northern hemisphere, and we have a flux tube which has positive toroidal field, which means it's pointing inside the paper, into the paper. And it's easy to see that such a flux tube, when it decays, would give rise to clockwise lines of poloidal field in the northern hemisphere. Now, if you just look at it, clockwise lines of poloidal field and a positive magnetic field will give, if you calculate the product A dot B, that product will be positive in the northern hemisphere. However, if you assume that the flux tube is trying to cut through the carpet of this poloidal field lines which are being produced in the same cycle, these poloidal field lines will then wrap around the flux tube in an anti-clockwise fashion. Now, if that happens, then the sunspot which finally rises to the surface will actually have a negative helicity in the northern hemisphere. And this argument can be easily extended to the southern hemisphere. So now, now we'll try to do a simple back of the envelope calculation to estimate the magnitude of helicity expected from such a model. So suppose phi is the flux which is accreted by the rising flux tube. So we assume that this poloidal field, the average value of the poloidal field in the convection zone is something like 1 Gauss, and the depth of the convection zone is 1/3 the solar radius. So this is the amount of flux that will be accreted by a rising flux tube. And then if this flux gets smeared in the entire active region, then the current around that sunspot would be given by this poloidal flux divided by the square of the flux tube radius. And consequently, the twist alpha, which is just the current divided by the value of the vertical field, will be given by this flux here. So B phi, depth of the convection zone, the magnitude of the vertical field, and square of the flux tube radius. Now we just plug in these values of B phi average of 1 Gauss, and sunspots have typical fields of 3000 Gauss. And for flux tubes with radius of about 2000 kilometers, we expect this alpha to be of the order of 2 into 10 raised to minus 8 meter inverse. Whereas for a sunspot which has a larger radius, 5,000 kilometers, we expect this twist to be smaller, of the order of 3 into 10 raised to minus 9 meter inverse. And these values are actually comparable to the values given by Canfield and Petzoff in their paper. So one direct conclusion from this simple calculation is that we would expect bigger sunspots to have smaller helicity and smaller sunspots to have larger helicity.
And I should interrupt because we are now at 11:45, which is the announcement of the Nobel Prize. We just have a short. I mean, for those people who have not been who are not regularly in Stockholm at this time of the year. What do people feel about switching to the Nobel announcement at this minute?
It's okay, but not yet.
Everybody.
When it's starting now, or
It's starting now.
Yeah,
Yeah,
sure.
let's take it out.
Okay.
And I take it to him, yeah?
Yeah, yeah.
Yeah.
Fine, yeah.